So we're abandoning the query caching idea?
Okay.
Changing
Same
idea?
ID, which not cache knowledge, cache instance.
So what do we got? He's gonna wow me with formulas. He's gonna wow me with formulas. Let's see what we got here.
Not really.
Let's see what kind of tasty formulas you got for me to snack on. Any better markers?
This is yellow.
See, this is the downfall of our department right here. No markers. How are we supposed to share all of this knowledge? Here you go. Here's black. How are we supposed to share knowledge amongst our peers? Ridiculous. That and portable chairs. It's amazing we even have computers at this point. I'm surprised. We're not here with abacus and stones.
Alright.
What's that?
It's kind of basic.
More with the explain and less with the excuses.
Gotcha.
I'm not feeling confident in your model since you don't seem very confident in your model. So you did bring me something here. I see multiple pages with scratchings on them.
Yes.
Alright. First of all, save our marker. Alright. That's all we got. That's the extent of the entire department right now. Alright. Don't talk about the formulas. Tell me what you're talking about.
So, interconnected network, just random amount of nodes have random amount of neighbors, but they'll have an average amount somewhere in there. And when you look at it from the standpoint of the query, the view of the query, it becomes a tree. It's a K tree.
Okay.
Just with random amount of neighbors per node.
Okay.
I was working with the averages, so I was just assuming there was an average amount per that I could just
First of all, what is our goal? Our goal is to optimize queries in a peer-to-peer network?
Right.
Okay.
Try
So what's the problem?
problem is well, I was using the Mozilla network style query.
Okay. Flooding?
problem being it takes forever when you flood a lot of nodes.
Okay.
So
So we want to approach a smaller number of nodes with the same amount of return. We want to transmit fewer messages.
right,
Correct? Okay.
or just stop flooding down the line.
Whoa.
Because it's exponential once one node sends it out to all its neighbors.
Right.
And those neighbors send it out there. So node 1 stops the
Well,
request.
they send it out to their neighbors, and their neighbors send it out unless they've already seen the message. So it's not. I don't know what the model exactly looks like, but it's not exactly exponential, right? Okay. Okay.
So
But inefficient is our claim.
originally I was thinking cache files.
Okay.
But more scalable is just cache the indexes to who has the files.
Wait, cache what?
Cache a reference to who has which files.
Okay.
And do that by percentage. Like, I'm assuming some files or
More
whatever
popular.
are going to be more popular.
Right.
They're going to be used the majority of the time. At least not
Okay.
more than half. So for a large enough percentage of all your files, some will definitely be used more than half.
Okay.
So you can find
So now, as far as so what we're worried about is the number of messages and whatnot, and you're saying cache. The problem with caching whole files. You said there was a problem with caching whole files because
it just becomes too large.
it becomes too large. Okay.
Some machines may not be able to handle it. I know the theory is everything equal.
Right.
But practically it's
Right. Well, no, we assume heterogeneous nodes. Like some are more powerful than others, some are more storage. Okay, so let's look at the proposal. What's the proposed system here? So so we're still sticking with caching, only we're caching references as opposed to values.
Right.
Okay.
So
What analysis do we have here?
this is analysis of seed time for any random given tree, depending on
Okay, so by seek you mean the search of
right.
the execution of a query and returning a reply.
Exactly, the first reply. That's where it's B representing the number of neighbors.
So this is only for first reply.
So that should be the longest it goes, like to the furthest neighbor by the time to live value where it's found.
Wait, what is the?
This should be like for if you have a time to live at 8, it should go 8 hops.
Okay. And
For
reach.
one trace.
Okay.
So assuming the average is half that.
Okay.
And 8 represents the time to actually send it on the wire and the node to process on the wire. Or before.
Okay. Well, let's start at the beginning.
Okay.
Okay, so we're saying A is the value processing time plus send time. So this is the time it takes to evaluate the query and send where?
Where's the time it takes from the send for it to receive it and then
And process it. And nothing else. Not reply or anything.
Well, processing or full.
Okay. So the reply is also okay.
Because assuming if it's a file, it's going to be non-trivial. You can't really factor a file transfer.
Oh, no. If it's a what?
If it's like a file,
Right.
it's like non-trivial time.
Right.
There's time involved. You can't really keep that at a time. That's not my concern.
It's how long you're not concerned with how long it takes to
Transfer.
send the file. But I mean, you are concerned with how long it takes to send a reply, right?
Right.
Because one of the problems, like with, for example, flooding, would be you send out a query. One of your problems is getting the query to as many nodes as you want to touch to process the query. But the other thing is that how do you control how they reply? You see what I'm saying? In other words, as you touch more nodes, there's a potential that more than one of them will have the answer, and all of them trying to answer will also be a scalability issue, right? So this processing time plus send time, does this include anything like that, like a reply? This is more the idea of finding a result for the query, right? And then we can work out how long it takes to answer the person. Okay, so A, so we have A. B is what? number of neighbors
Right.
for individual peers.
Average number of peers. It could vary.
Right.
One guy could name one, another guy could name 8, 20.
Okay. Well, it could vary depending on the network that you're using.
Right.
Because some of them might be fixed, some networks. But this is for an Nutella style network, which is what, distributed hash table? That's how they track their peers. But okay, so we have a number of neighbors, an average number of neighbors. R is time to live for the query. Okay. Average seek hops. So this is the average, what? Average number of hops.
Average number of hops per, just like you followed one trace that would go until it found the file. Or not just one, but the average it would take.
Okay, you're saying
So
this is
I'm
R.
assuming even distribution of whatever.
Okay, so we have what? Explain your terms here. You have B. That I assume is the first one, and then for every hop, you're saying for every hop there's B squared.
That was the maximum number of.
Right, neighbors. That's at the maximum. Hold on. I'm just trying to think if that's right. RB squared. Well, I have B. I mean, the idea is I have B neighbors. They have B neighbors.
Right.
That should
So
be
it's
square
also-
term, but
For each number of.
it's not B to the. It's not something along the lines of B to the R. Or B to the hops or something. Because you should be exponential
Right.
as you go out, right? B squared becomes B cubed becomes B 4, right?
But then there was a problem. There's B there plus 1.
What's that?
B there plus 1.
Something along the lines of B to the.
I couldn't remember what the tree was called when you have multiple nodes.
Oh, okay.
Is it K area? How do you determine how many nodes are in a tree
No, wait, because they all cancel out.
How many nodes are in a tree?
that have more than 2?
Is it like K tree or something like that?
Yeah, it is. He said it's a K tree.
And what are we trying
This is
to
the
find?
number of
runtime?
layers in a K tree. Is that what this formula is?
Isn't that just log n? Isn't it the height of the tree?
No, that's for binary tree.
Oh.
It's not like something like log base K. I don't know. Okay, well, I mean, I'll believe you if that's a K tree's number of
I approximate.
levels, right? What's that?
I approximate. It works for small ones. I was going to go back.
So we want this average C cops to be the height of the K tree.
Basically.
So,
Or half.
well, you want to say half that because you're saying that you're hoping on average, after getting through half the tree, you'll find it. Is there anything to support that? Because the tree has a wide base, right? In other words, the bottom of the tree is bigger than the top of the tree.
I'm not saying half the height, sorry, not half the height, but half the connections.
Right. Okay.
So wouldn't that
I'm
just
a
be the number
node.
of nodes?
I'm a node. I query. Now, a hop, you're saying that at the first layer, me sending to all B neighbors is B hops?
One.
Is one hop. So one level is a hop. Right?
No, yeah. It's the B.
So B. So you're saying that is B hops.
Right.
In other words, you're counting each of those,
Each send
each send as a hop. Okay. So what you're saying is half the nodes in the tree, half of the number of nodes in the peer network is what you'll have to query on average. All right. I'm just wondering how useful this value of average seek hops is from the standpoint of this. We can see how important the first B is because basically the aggregate of all the communication of B is what we need for the pipe going into the peer that's the originating peer. But the second you get beyond that, the number of hops, the relevance of the number of communications diminishes. Because once we've distributed the first B, we have B different independent communications at that point. You see what I'm saying?
Yeah.
So whether or not this value, this calculation of number of sends, this number of messages, this average number of messages, is true or not, I think it's important to note which of these communications are between the same two peers, right? Because that's, in other words, 100 different communications between 200 different peers doesn't concern us, right? Well, I mean, I guess it increases the overall communication, but that's very different from 100 communications between one node and 100 different nodes. You see what I'm saying? I mean, that's significantly different in the sense that, in other words, like if we had a tree, let's say, and it's a peer, all its neighbors, with all its neighbors, with all its neighbors, and we consider this tree to cover the peer-to-peer network. Querying all the nodes in that tree is basically covering the tree, right? Calling all the edges in the tree, saying that in some way we communicate with all of the, we're calling all the nodes, right? In some way touching all the nodes, okay? There's not a way around that, right? There's not a way around touching every node. If you want a complete query where you touch where you are sure of whether or not the file is there or not, you have to touch each node, right? But the problem in peer-to-peer is not touching every node. It's how do I touch every node with the least amount of communications, but even more than that, the least amount of communications over the same link. So I think we need to think about that.
Maybe not the best.
About that value. I mean, the significance of that value, and is there a more complicated metric that we need to measure there? You know what I'm saying? So, okay, so this is good. So this is something along the lines of the number of edges in a K tree, and half of that. Okay, now the half. What do we think about the half? Okay, the half is awesome if the half is, that's what we need to color all the nodes. Okay? The half is hopeful if the half is what we think is, we think we only have to color half the nodes, touch half the nodes. And I think that's touch half the nodes, isn't it?
Yeah.
So where did you get b plus rb squared? What is that? Where did that formula come from? Is that number of?
That's like guess and check.
Huh?
That was guess and check.
Okay. So let's find out the formula for the number of nodes in or average number of nodes in a K tree. Right? Now, what do you want the half to be? You want the half to be a hope that I only have to talk to half the nodes? Okay. So we have that. We have half. We have a hope that we only have to talk to half the nodes. What about the hope that, or what about the goal of not?
It was the half was statistically probable. It's on the first node and the last node.
Okay, you know, I understand the hope of it being, of only having to ask half the nodes, and that's cool. That's fine. But what I'm saying is, can we get more? Can we lower that number even further by? I mean, one of our goals is to lower the number by not sending as many queries, right?
Well, this is the base case, not my.
Okay, yeah. All right. So this is what we want it to do. We want it to be half. Talk to half the nodes in the tree, right? Okay. So average seek time, you're saying is processing time plus send time. Okay. Big problem is the send time, because the send time is a function of queries you're sending out. No, not just the bandwidth or not just the communication availability. Send time is very dependent on how many queries a node is sending out. In other words, you can make it so that nodes are sending out fewer queries, your send time is slower, right? So that's a difficulty in that average seek time. Okay, and the average seek time as a function of z, which is what?
Z is the probability that the file will be found on any given node.
Okay.
Or an index.
Here's what I don't like. Is you already included a factor for the probability that it's found on any given node. I'm saying there's a 50% probability that it's found on with the half. You're cheating. You're getting two probabilities involved that
May or may not.
if you're gonna be z, if you're gonna use z, you should take out half. Right? Because half was already a hope that I'm gonna see it on 50% of the nodes. The idea is that you should not make the average seek hops the average. You should say that's the limit, right? But by introducing a probability, you are introducing the concept of average or probable or whatever. So I mean, is your hope that like we can adjust z
Right.
by caching?
Improve Z by caching the indexes.
Uh-huh.
And then time goes down.
Okay, so we need to take the half out, I think, of anything that has to do with the number of hops, because z becomes all of our average, right?
Right.
And I mean, if automatically without adjusting z, like if in use we get half, then z starts off higher. You see what I'm saying? So we're not losing the half. We're just
Still
saying
built
it's built into z. So if you're saying I need to improve z, if already just out of the box setting up a peer-to-peer network you get half automatically, well you get to start improving z from 0.5. You see what I'm saying?
Yeah.
So and your idea is that by caching I actually increase z beyond that. Okay, so average seek time as a function of z is, let's see here, 1 minus z. So this is the times, what does z represent? Z is the probability that it's there or not there?
So this probability it's not there, which is the time. Just
Okay. Let's log b plus rb squared. Okay, b plus rb squared is the number of, that's the height.
right. So it's the thing.
All right, so this is going back to the idea of this is the number of hops as far as height goes. Now, I don't know. I think the biggest thing is tying in. Okay, and now your whole thing rests upon just improving z. So this formula is some sort. Your claim is the metric for
Right.
what happens when I query, given the probability of a query being answered on a node z, and then so separately from this, we're going to do manipulations to the network to say this should increase z by x. That becomes something in this function of z that lowers this seek time. Now, all right, the model, we need to, send time needs to be related somehow to, see this idea of, in other words, the deeper in the tree you go, the higher you are in the tree, the closer you are to the root, to the originating node, the more important,
That send time should be.
the larger the send time should be. The send time should get bigger as you go to the top of the tree. So the goal should be getting to the bottom of the tree, or like out in the tree quicker, or in some way that balances how many people you have to talk to before you can distribute. And then the other thing is, okay, so this is good. Okay, so this is good. So the idea is we're trying to have some analysis of how many messages are passed, right, between nodes when you query. So the idea is I want to touch all the nodes. The model is supposed to be some calculation that says this is how many messages are passed. Okay, and then you can manipulate these other things so that you can change how many messages are passed. So right now your formula is saying, by finding it sooner, we're going to reduce the number of messages that are passed. Okay. There's also another way to reduce messages, which is not sending any messages that aren't necessary. Because our tree is actually not very clean. Our tree is not a clean tree. It's not just a K tree where you have, some node. You have K neighbors. They have K neighbors because some of their neighbors are neighbors that you have. And so the thing is, though, is that I don't know what the tree looks like because as you get further down the tree, right, these neighbors actually become redundant because they're neighbors of other nodes, right? What ends up happening, I think, is the tree. See what I'm saying? Because while you may still have K neighbors, right, they actually go back up. So I don't know how that. If you don't model that, right, that it kind of diamonds out, that's fine. It's just all the numbers overall will be inflated, which is fine, right? Because if you're comparing yourself to something that's not caching, their numbers will be bigger too, right? So it'll all. I don't know if it scales relatively, but I mean, if it grows the same. I mean, as far as if they just treat it as a traditional pyramid-like tree. I don't know who loses more, or if anybody loses more. You know what I mean? So, okay. So next is the claim is how do we lower Z, or how do we raise Z? Sorry.
So some files will be using more than others.
Okay.
And for those, as long as you choose a percentage of total files or objects or whatever that's less than that large group that's used more than others, you can require each node to hold a small subset of that, so that when
Now, when you say small subset, do you mean, are there any other attributes to that subset that you want? What I mean is, can I choose any subset? Can I choose? Okay. The perfect subset would be everyone having a subset with no overlapping pieces.
so I was thinking just random distribution or something.
Okay. So random subset of the what? Of the most recently queried, of the most often queried?
Most often queried.
Okay, so now, if we're going to claim most often queried, that means we have to track all queries.
I was thinking from the view of the node, it'll differ, but overall, it's still going to be, like, there'll be a fair amount of overlap to who considers, let's say, the top 10% of query. Probably everybody's going to see that it's about the same. Maybe the top 30% will be varied.
I mean, do we know that? Because, alright, that's true if we made sure we talked to every node on every query. I mean, they'd end up leveling out, where everybody, if they just choose the most often queried things from their view, that would be a global most often query. Like, in other words, they'd be selecting from the most often queried global query, like from the global queries. I don't know how true that is, because the assumption is that you'll see about the same queries as everyone else, or at least some. You see what I'm saying? You're going to see a portion of the queries that everyone else sees, and if you choose the top of yours, it's going to be in the top of all the queries. But, we have all these claims of, like, not wanting to see all the queries anymore. So what you're going to have is, if you think of the space of queries as like a landscape, right? There's all these local minima that we can't know what the relationship between minima are until we zoom back and look at other pieces. Which is honestly, that's not bad because local minima in these types of problems are what we shoot for. Because having global global knowledge is what we're trying to stay away from, and it's something that we can't. No, I mean, what I'm just saying is that finding your local minima is a good thing. Just it's better than not, finding the local minima. But I don't know how far we can go as far as claiming
That will.
where that is compared to the global minima. And most distributed algorithms, especially heuristic types of distributed algorithms, like all these, we get into this world that's outside of the algorithm people's world. The algorithm people like to calculate and say, here's what's
exact
what,
time.
or it's like, or even if they do things that are kind of approximation, they're even saying here's how approximate it is and stuff. Here's what it is compared to the global problem. Us fuzzy people don't care about all that. We just guess, So it's like we just like to guess. So the idea is most of these like fuzzy types of things, like where you kind of are guessing whether it's genetic algorithms, neural nets, SVM, or any of these kind of learning types of deals or heuristics, you're just finding local stuff. There might be this varied landscape of here's high values and low values and high values and low values. We just kind of look. We just kind of pick a random direction and say, okay, here's the lowest value in the random direction I look. Okay? But there's this thing of like you can't. How the landscape is built kind of precludes you from finding out the global because you can't get over this peak. Because what I mean by this landscape is, if you think of files like that you see, queries you see, you start getting this plot, right, of all the queries that you're seeing, okay, and then you start seeing like frequencies of these queries, and you're trying to say I want to find the highest frequency, of all of the queries, so that I can keep those. Because if I keep those, I have the highest probability of getting hit anytime I'm querying, right? Because the highest probability of that query being this one is at that peak, right? So if I have these peaks and valleys, that's my view. But there's an overall landscape out here that has the highest of all the peaks, right? But the problem is that when I'm looking around here, these minima make it so that like you can't jump over the next hill because you're kind of just looking here, and this is highest, this is highest, this is highest, and then when you get to here, it's like, oh, I'm still higher. I'm not going to go down there, right? I'm higher than this peak, so I'm going to go ahead and stay over here and not traverse over there. Because if I were to traverse over there, I might as well go all the way across the landscape, right? So that's what I mean by that's what happens with these kind of guessing algorithms, is the idea that you get to these local kind of highest mountain, right? But then you don't realize that there's somebody over here laughing at you because your mountain is really, really tiny compared to like what the actual global minimum is. So, but our hope is that in a tree like this, your local minima, there are no little kind of boundary types of mountains that are blocking you from seeing a large enough picture to say this is a good choice. But I mean, the main thing is being careful about claiming something like that. You know what I'm saying? Is the idea that we are looking at local maximum, but we're looking at local maxima, but we're not seeing the maximum of the whole thing. But the whole goal is to not look at the maximum of the whole thing, because if we were to do that, we end up back at the basic scenario of just searching everything. But we need to figure out what that is, like what that looks like. But this is a good start. I mean, this is a good start of a model that lets you know. I would call that hops. I call that number of communications. The time, I think we need to find some way to relate the time to the number of messages from a single node. Right? So, well, I guess it's always going to be B, right? If we're always sending to all the nodes. I mean, if we're not going to, there's, like I said, there's two ways to lower the number of messages. What were our two ways of lowering the number of messages?
Either send
What do you mean by that?
If you know nodes already received that message, let's send it.
Okay, so reducing the number of messages reducing the number of redundant messages, and what else?
Sending perfect messages.
What's that?
Sending perfect messages.
No. It's funny because the other way is what you're trying to do. Is right? Is make it get found sooner. Right. So okay. So those are the two different ways we can reduce the number of messages. And if we're not going to address the other one, which is not sending redundant messages, then we may be able to leave a constant, right? Or an average, or regular, not as a function of the number of neighbors. But I don't know. I think there is still some relationship between, as you get deeper in the tree, B shrinks, right? If not through directly seeing that this other person already got the message, at the very least, when you do send it to them, they'll stop, right? Because you'll have some sort of in all these things, you have like a identification of the query, like some tag, some ID number of the query, and you just keep running like a recently queried list of tags, not in the sense of your cache, but just I just sent this 2 seconds ago. So if I see it again, I'm not going to send it again, type of thing. So at the very least, you'll have that to stop you from sending a query that you just sent. Otherwise, you get into broadcast storms and loops and stuff, which I mean, if I'm not, I don't know if I think Nutella probably does exhibit that in a lot of ways, but you start getting into those loops where you keep sending the same thing. But even even most rudimentary systems can at least start stopping that, especially if it keeps happening over and over. You can at least keep the last few and say, okay, I'm going to stop sending.
Like message flooding?
Huh?
Is that what you're talking about?
Yeah, we're talking about flooding.
Okay. Yeah, then Nutella, it just keeps a count, doesn't it? It only allow like 10 levels of like recursion or something.
Right, but so you just basically you have to track what you've sent in some way, whether it's how many hops or an ID saying that you're not going to do it again, or a time expire. I don't know. You're saying that it tracks hops?
I think so. Like each time it's like, because like if it's recursive, you'll ask this guy and he doesn't have it, so he'll ask someone else.
Uh-huh.
That's like I guess that's one hop, and then it only has like there's like 10 hops, I think, something like that.
Well, that governs the diameter of the network, right? That says I'm going to go 10 levels out. But then just having an idea of what the query is and an idea of it and keeping track of it is what prevents the loop. Because it's real easy to say, okay, when you're one hop out, you can say, I send this, that person gets it and says, oh, well, you sent it to me, I'm not going to query you again, even though you're a neighbor. But yeah, 2 hops out, once you get to the next person, if they're also a neighbor, then they can loop back, because they don't see immediately that you are actually the originator of who sent it to the guy who gave it to me, right? You think you got new info, but I'm like, you're like 2 weeks behind me.
We just went over this in like networking too, with routing, how to like deal with that shit.
Right. Well, see, like routing in general is actually easy because like whole swaths of who's on the other side. In other words, there's identity in a.
If you have no map.
Yeah.
Yeah, I think it was for local maps, right?
Yeah. So like, but there are still broadcast norms, and you usually do things like spanning trees and stuff like that, where you see when you can acquire global knowledge. These are all trivial problems, right? It's like we have spanning trees and all kinds of stuff to prevent people from just flooding everything, right? So, I mean, the real problem is that we don't have any global knowledge, and in fact, we don't want global knowledge, right? So we need other ways to do it. No, but I mean, even the most rudimentary system of keeping the last X number of queries just in a little buffer, just so that you don't rebroadcast. But what I'm saying is the end result is B shrinking, right? So if B is shrinking, how does that affect our formula? So if B is shrinking, the RB squared value starts shrinking.
Let's say it would be like this is building up to half of what I thought it would be, and then it shrinks back down to 1. So it's
Wait, what now?
if this were half,
Right.
then it builds up to half, and then it shrinks back down to 1. So
that diamond.
This, all those,
Yeah. And then there's a calculation that you say what the whole thing is. Usually ends up being some sort of like 1/2 something, because you start at it. It's basically the width of the tree is shrinking as you go up, so it's kind of like log and then log. So you add enough logs together, it ends up being half or something like that.
Silly
I don't know. I don't pay attention to any of these things. So these are all things that I knew at one point that I don't know anymore. But what I'm saying is that B is changing. Even the most rudimentary system should be able to shrink B as it goes down. And how does that affect what we're saying here? In other words, you have fewer nodes that you talk to towards the end of the tree. B gets smaller as log B gets bigger for that log of all that junk right. In other words, as the number of hops, in other words, as you go further out in the diameter of the network, you should be shrinking. Even though that's counterintuitive. I think you have to know how fast are you shrinking compared to how spread out, in other words, how wide the tree is. And that's probably related to how many neighbors everybody has. And I guess one question would be, what does that look like with perfect distribution? Like completely random, uniform distribution of peers. In other words, how many peers that I overlap with somebody. If I have good distribution, it will be at least the same. In other words, the number of neighbors I have in common with any given peer is some factor, right? And it's always that factor among everybody. And what does that number look like? In other words, as I get to X number of nodes wide, right? Like the first level, I get B. B different nodes, and we know they're different nodes because they're all the neighbors of just one peer, right? I have B different nodes that got a message. Now, there's some factor of all those B nodes. That guy has actually B minus epsilon neighbors that will actually need the message. Its neighbor has B minus epsilon. Its neighbor has B minus epsilon. Its neighbor has B minus epsilon. We don't really have an idea of how much of that epsilon overlaps with other epsilon, but we're kind of B minus epsilon.
Somebody epsilon.
So what I'm saying, B minus epsilon squared is the next level. Right? The level after that will be B minus, what is it?
Epsilon squared cubed.
B minus epsilon squared times, yeah, so B minus epsilon cubed. In other words, epsilon is growing as B grows.
Right.
Or as the power grows. As the power grows, epsilon is growing, which is reducing B. You see what I'm saying?
Gotcha. And
so the question is at what point does epsilon make it so that it's zero? In other words, you get back to the other point of the diamond. B minus epsilon. So the power n, which is n is the height, the diameter. And then n can go up to some factor 10, something like that, to say that's the maximum diameter of the network. Then you got yourself a model. Huh?
Okay.
And then you see what Z does. And then you also see what... See, this type of thing is awesome for simulation, because you can just make stuff up. You know what I mean? You just make stuff up, but, the thing about models and the thing about simulation is you really got to know what each of those factors does, so that when you change them, you know what's going on. So, like this epsilon idea, you can kind of say, oh, okay, well, because epsilon probably isn't uniform. You know what I'm saying? Just realistically, if you're in a peer-to-peer network and you kind of peer up with somebody, there's actually a very good chance that you share a lot of the neighbors that other peer has, just from proximity, if not proximity. And there's locality issues where you probably gravitate towards knowing more peers who have files like you, or that kind of thing. So, but your model becomes more powerful if you know what epsilon does, because now you can say, oh, well, if epsilon's a function of, epsilon is actually very large because of locality or something. Here's what happens to my network. But what I didn't think of is on the other side of that means that Z actually becomes more difficult, because the more locality I have, where the more peers I know, in other words, the more I hang out with people like me, the less chance there is that I'll know something that we don't like. In other words, if I'm querying for, if I'm always querying for rap music, there's just, and so that means all my peers have rap files and stuff like that. When you ask me for a country western song, Z becomes very small that you're going to hit it at least within my circle. So there's actually a greater chance that you're going to have to go beyond that portion of the tree. Oh, I like it. And it's always shocking to me when one of you demonstrates that you were thinking about something. I know, look at that. You even has papers with stuff written on it.
I know.
Like with a pen.
Oh my god. Ink even?
Yeah. No, that looks good.
Way to go, buddy.
Now, here's the question. Are you going to write me some simulation of that?
Ooh.
I really would like to. But there's like 3 weeks.
Right. There's 3 weeks.
Yeah.
But what's that? Some lists. Some linked lists.
Big deal, man.
Just some linked lists and some counters, right? How long should it take to simulate that? I mean, you got
All time world, dude.
because you know what? Here's what you do with this Z. What's the point of simulation? Okay, the point of simulating that. Here's the point. You have these formulae, right? You have a bunch of formulae that you say, okay, I claim, this is how many messages are sent in a query. I claim this Z, as I increase it by, as it increases, this is what happens to the number of messages. I claim that by storing this many or percentage of queries that I've seen that have the highest, frequency or whatever, I claim that if I do that, if I store those things, Z goes up. So my total claim is that by storing these queries that happen so often, my claim is that the number of messages goes down significantly. Okay? So that's your claim, right? And you have these nifty, fancy formulas, right? Now,
Okay, if I actually screw it up and then it doesn't work out?
absolutely not. No, I'm just kidding. No, that's fine. But if you screw it up in the right way, is when it's fine. If you screw it up in the wrong way, it's not fine, right? Because otherwise that opens the door to people just screwing up by default and everything's fine, right?
Looking at me.
I'm just looking at both of you. It's you're spread out. I have to. It's a lot of turning.
Like screwing up.
Okay. No, but all I'm saying is no. Your theory not being correct is fine, right? As long as you tested the theory, right? And as long as
That's what it's saying. Testing.
right, and as long as your models are modeling what you think, as long as your theories are your claims are actually being tested, right? And all those things, it doesn't matter if your claim's wrong, because you always prove something, and what you'd be proving is that this is not true, right? Is that by storing these things, what do we learn from that? We learn things about like the problem space of these local minima. They're no good. They're so unrelated to the global or the local maximum. These local maxima, they're so far unrelated to the global maxima that it doesn't make sense to keep that knowledge. To store that knowledge. Okay, but anyway, the whole claim is that by caching certain queries, I am going to reduce the total number of messages. Okay, now you are actually starting off at a place where you have an analytical model that you think is good. So that's actually another claim, in a way, is that my analytical model makes some sense. So those are two different things. Now, you might want to do two different things. One is,
Section 1 of my model. Section
no. Paper one is, here's my method that I claim, and here's a simulation of that, and here's some numbers. I learned something from that. It's good, it's bad. I learned something about the number of messages that are actually passed, yada, yada, yada. Paper two is, here's an analytical model. Does that analytical model actually match? Because from there, if it does match, you can actually test other hypotheses using the analytical model as opposed to simulation. You see what I'm saying? Okay. Simulation is often easier, especially in complex behaviors like this. Okay. So what is simulation? You put together, you write a little bit of code that says, here's a node, here's the peers that it has, here's a query. I'm going to go iterate through the list of peers, ask them all. They're going to iterate through their list of peers, ask them all. And through all this, I'm keeping counters on how many messages were sent, how many messages I see, probably through tracking the queue that you're dropping stuff in to say, this is a message, that's a message, this is a message, right? You keep counting everything up, right? And then what you start doing is you say, okay, run 1,000,000 different random queries with 1,000,000 different random peer configurations. And then what you do is you start plotting that, right? You say, this many peers on average does this many messages for a query, this many peers, yada, 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 and you keep plotting that out. You add in your little caching mechanism, and then here's where they are on average as the number of peers grows, right? So you have these two plots of data, not plotting a formula, plotting data. And then what the typical thing that happens is you do that, and you start seeing what the formula looks like. And then you go back, and then you create that kind of analytical model, and then from there on out, you can just test the analytical model, right? Or the analytical model can tell you, what do I need to improve in order to reduce the number of messages? Yeah. And the only problem is that oftentimes these simulations that you do are actually modeling very nonlinear behavior, stuff that you can't necessarily put easily into a formula. So there's always this, once you create the analytical model, is it really modeling what actually happens, right? Because what ends up happening is you write the simulation, you do it, and occasionally you'll run it and stuff, and then you'll say, okay, this is all cool. This caching system's awesome, and it reduces the number of messages. My queries are better. But then, so then you pop that into a peer-to-peer network, and it's slower, right? And your queries don't work as well as they did before. So what is that saying? There's a factor that you're not modeling in the simulation, which also means that the analytical model you built off that simulation, there's a factor missing. Okay? But the beginning is to me, I don't know, it's just, some people doing the analytical model is a lot easier to start. Okay, these are mathematicians, graph theory people, all these people love doing models first and then comparing them to whatever happens. They'll build the analytical model. They might put together a simple simulation and see if they match up, because they're more interested in making the analytical model. If you're more interested in creating a solution to a problem like the caching thing, then you usually go the other way. You create a simulation, see if you reduce that, and then kind of as a side effect you create the model, because then you can start doing more analysis. The model becomes insight into how do I solve the problem, as opposed to the modeler who says, I want analytical models of this whole behavior. Okay? But it's good. It's good. But I mean, like I said, I recommend going the simulation route. Build a very simple simulation of really just a counter. It's a way to count messages given these factors of here's how many peers there are. Some of the peers may or may not be, may or may not be redundant or whatever. Okay, but you build a very, very simple kind of peer-to-peer simulator, right? And peer-to-peer simulator is really just one message sent, two message sent, three message sent, and you keep going until you get a hit. Right? So, what do you put into a simulation like that? Nodes, right? You got node objects. Those node objects have a list to other node objects, right? They have a list of target objects for queries, right? You have a list of target objects that represent all the things on that network, and then you have a list that each of them are holding, and they rank. Each peer has a certain number of objects that they have. Right? What else do you have? And then so through the peers having a list of other peers, you've already created the network. And then you have some methods for querying all your neighbors. Okay, so separately for controlling the broadcast, so you'll need another little list of the most recent broadcasts.
If I just send out one query at a time,
Won't work.
so I'll put the most recent broadcast.
Yeah. No, I mean even if you send out one query at a, oh, you mean you're saying one query at a time, and if you ever see it again, don't
One query at a time, flag,
a flag that says I've sent it.
and then just don't mess with it.
Why don't you do it right?
Let's start small.
I mean, how different is it doing a flag and a queue? One little tiny piece of code, right?
It's like Java 1
Huh? I mean, that's the beauty of object-oriented networks. I mean, object-oriented programming, right? What's a queue? New queue, right? What's a boolean? New boolean. What's the difference? Right? Boolean equals false. Oh well, queue, right? NQ, done.
I love that Java.
Gotta love the you know all the fancy Javas and your hoo-has. Okay.
I got used to C.
Do it in C. Do it in STL. Do some C++ STLs. Come on. Just queues, booleans, what? All right. So you got that. So how do you set up a simulation run? See?
Random nodes would initiate a query.
No. You haven't even built the network yet.
Well, you have to.
All right. You create n nodes. All right. You take b of them. You randomly select b of them and assign them to each of the n nodes. Right. Random b n assigned to 1. Random b assigned to 0. Random b assigned to so and so. Random b assigned to each one. Right. So choosing from the total pool of available nodes, you randomly select your average b, right? Not necessarily b, but an average, but a number that averages out to b. Okay, so you choose b of them, pop them on this one. Choose b of them, pop on this one. Choose b of them, pop on this one. If you're very thorough at that point, you'd also at that point just check for fun to see if you have a fully connected network, which is interesting, right? Okay, so you created your network by doing that, by selecting the random b, right? Now, what? You create m different objects, right? Randomly select a few of them, put them on node 1, few of them, few of them, few of them, right? Then, okay, so now your network's set up. So, a random query would be choose a random node, choose a random object, have a query. Run it, count the number of messages that are sent, and do that a bunch of times. I don't know. How much does it change? What's the actual bunch of times that you do? If you really wanted to do it right, is you'd watch the number of messages, right, and keep track of all the numbers of messages that you created, and when the standard deviation between the number of instances you've seen and the mean of that and the standard deviation. Once the standard deviation gets small enough, you'll know the actual mean, right? The idea is this. Every time you run one of those simulations, you're getting a point, which is estimating the mean of all the different, of how many messages are sent during a query, right? If you get enough of those, you'll create a curve, or an area, right? And then that area, the middle of that, actually represents the actual mean of all possible queries. So, how many do you do? Well, as many. If you really want to do it, you'd look at the standard deviation of the mean of all your samples versus, and then once that gets small enough, you say, okay, I'm done. But I'd run it 100 times, see what it looks like. Yeah, at least have a better idea at that point than what you did before. Yeah. And then what you do is, then you just have those things implement your method, right? Which is every time I see a query, right, I am going to track, I'm gonna keep that query. What is it you're tracking anyway? Who answered?
Well, honestly, when I was thinking that when our node receives,
Wait a second.
a node knows that when
He's trying to trick us. I think.
the node who has it responds to its neighbors and back down.
So we flood back upstream. That's a trap. See? It's a trap. Because you didn't have to do that before. Now we got a trade-off, right? If you can reduce the number of queries, how much does reducing that number of queries counteract the fact that you're flooding back the response? It's a trap.
Trickster. Try to pull a fast
I
one.
know, he did try to pull a fast one. There's another mechanism that needs to be in there in order for anybody to be able to cache anything. Oh, it's a trap. Don't flood back up. Store answers that you've had. That's it. What I'm saying is this, is because the person querying changes often. So if you just store answers that you've gotten, you can use that as shortcuts in the network.
I just know who I got it from.
So when,
Right.
So when you
So if you ask me for, if I end up getting a query where you ask me for it, I already know the answer. I already got the answer, so I'll shortcut. But do both. See what it looks like, Or pick one. I mean, look at whichever one's easier. It's like, because that's the first one you'll have an answer for. And you say, oh, that's actually a pretty interesting answer already. I'm done. I'll do the other stuff later. But yeah, that's a trick. It's a trap. See, it's tricking us into flooding the other way. It's creating more flooding.
When do you get my second page of math?
It's fighting
What's
fire
your
with
second
fire.
page of math? You don't have any more formulas.
Oh.
It's nice and neat.
Oh, that's just words.
He wrote out the numbers 5 plus.
Right? He wrote them out.
Yeah, that's why it looks like.
Well, no, I didn't.
Well, I mean, we're not. Nick doesn't have anything to say. What else you got?
How do you know?
What do you have to say?
I got a lot, buddy.
All right, what do you got to say? Go. You don't have anything, do you?
No.
Go ahead.
Well, this
Let's
was
see your
the-
second page of math. No. We were bragging about a second page of math all of a sudden. Now what? You're all coy.
Oh,
What do you got?
this is fun. Alright.
He does too much writing like in one go.
I don't know what it means.
You should like write a little bit, chit chat with us.
Okay. Whatever.
It's outside.
Actually, no. Write all that stuff up. I don't hear about.
I've been mega bombed like the past 2 weeks.
You know what? Let's do it.
Mega bombed with this stuff. I haven't done like crap.
Oh yeah.
Everyone noticed, I'm sure.
I'm scared of what I have to do. really don't want to do the dynamic loading for.
Is that the Pace XML thing you saw? Wait, I watched the video last night, like kind of half of it, and
No,
I saw the
it's,
snide remark he made, where he's like, "Nick, yeah, that's you. If you're watching this."
No, it's
Wait, dynamic loading.
for the restart.
Oh, I see. Yeah. No, I started working on the console again, and I realized that like I didn't really implement the threads right. So maybe it's like I need to make a different input output.
Trying to get it all done today,
Man. Whatever.
I saw your meager check-in.
Last night.
Yeah.
I know, because I
That
didn't
was
get
awesome.
home until like
I
2.
think you like put some print out some system print lines.
No way. I added a new group and I started how to start it. Like so you can add multiple groups. Like just keep popping them in, and then you can start which one you want.
Right.
I don't know if it works yet.
I don't think it does. There's no
Uh-uh.
loop. You could do it once.
Yeah,
Need a loop in there.
I know. It was late, man. It was like 4. I was like, screw this, I'm going to bed.
Yeah, last night it was late.
So this morning.
As opposed to the 2 weeks before that. Yeah.
And all those tests.
It all compressed into that one, like
Yeah.
like last night and
Yeah.
like
Yeah.
I know how it goes.
I know, right?
It's hard to bear the burden of 2 weeks of that little. Yeah. Oh my gosh! Look at him with his set. What is that? A set?
Where?
What he's got a set? So don't you mean the size of the piece? It's a piece of set.
He's just
Look at this. You're bringing in formulas and new techniques.
I know. I'm such a chump, right?
Broadening the scope.
Speaking of which, what's the deal with me signing up for this class?
I don't know. I'll talk to Dr. Penn about how it works.
Should I bother signing up? Would it be beneficial to my GPA?
Yeah, you can sign up so that you can,
Get the D.
hopefully this next semester you'll be able to produce something.
Yeah. That
No, I'm just kidding. You've done some. Look, you've done some stuff.
Some.
You've done
Not
some
much.
Stuff.
I'm not gonna lie. It's been pretty
All I'm
meager.
saying is I look. I have to look at the stuff that everyone's creating. I got formulas over here, and I got
Jokes over here.
I got some system print line, system out print lines over here. That's all I'm saying.
I actually did this because I didn't want to do the code.
Right. See?
I'm scared of the code.
I know, and he's got the formula. See?
Don't worry, next semester I'll rock it out, man.
I bet.
Taking easy classes.
That's why by the way, that's why I'm smacking down all your formula and stuff so that you can finish my code for me.
Right.
But go ahead.
Actually, I got 2 weeks.
See, last time, after the code, he's like, man, I don't even code anymore. So now I want to make sure he's like, man, why don't I even make
Why don't I
formulas
bother?
anymore? All right, go. All right, we got it.
All right, this is the set of the U. It's a set of queries you're tracking, like your top 4.
Your cache?
Yeah.
Okay.
So if the query happens to fall outside of that, you still got the normal window time, whatever it is.
Okay.
Unfortunately, if it does fall into this, which is
Hold on. Okay, give me what they mean.
S is the size of your set. T is the
Size of what set?
say you're tracking the top 40%.
The cache. Let's call it a cache. It's a cache.
Well, the cache is S. S is the percent that you're caching.
Okay, so S is the size of the cache.
Right.
Yes?
T will be top.
Top. So it's a cache of a cache. Alright. So you're saying that there is a top. Who cares what T is?
This is the subset that
I get you, but
you're limiting factor.
are we tracking T?
Yeah, everybody's tracking T.
Everybody's tracking T, and you're saying S is what?
X per, wait.
S is a percent of T. It's
What does that mean?
the upper echelon.
All right, it's the top part of T, but what does that?
I was thinking
What does that mean?
I was thinking the view would be more homogeneous if you use a smaller set, still sufficiently
What is-
large.
How many entries are in my cache? T
Yes.
or S? T.
T is the number. T is the whatever is part of T can be part of your cache, but outside of T.
T is the cache. Yes.
S.
S is the cache. T is not the cache. S is, you're saying, a subset of T. The problem, here's my problem. You see your diagram there? You see how S is inside T? You see how S is a function of T? Why are there two variables? You see what I'm saying? If S is always going to relate to T in some way, why do we need two variables? Why are there two sets? Why are we looking at too many things? In other words, if S is related to T, you don't need one of them. You see what I'm saying? In other words, if this number, S over T, for example, if as I change S, T also changes, or by setting T to something else, S will also be changed to something else, or S is some sort of percentage of T, that's one number. You see what I'm saying?
Gotcha.
Right? If you're going to make T bigger, but leave S the same size or whatever, S is still relating to T in some way. Okay? The only reason I bring this up is because I was watching something, watching another talk the other week where the same thing happened. There's this, there's these variables, and you look at the variables and you're like, oh, wait, but I thought that variable was related. It's a way to make more formulas. You know what I'm saying? But if they're relating to each other and one changing will also affect the other one and whatnot, you should reduce it and get back to your one variable. Okay, so S is what we're caching. But maybe your claim is that T is what? Some sort of global top percentage, and
Right.
S is something in there. In that case, it's not a circle in the middle, right? S is going to be some circle that we hope is within T, but may cross over into others. You're saying S is the cache, right? What you're caching, because your local view of the network says this is the top 20%, the top S percent of all the queries, right? Your hope is that S is a subset of T. You're hoping that S is the top subset of T if you were to rank them.
That would ultimately.
All right, that might be a reason to have T, but your diagram's wrong, right? Because you have no idea where S lies within it, right? You're saying S can't contain anything outside of T but within all. That's not true.
Okay. Well, hopefully.
That's a claim, right?
Well, then hopefully it can.
Right. But hope at $1.75 will get it right on point. All right. All right. So S over T is the percent probability that
Requiring
X over S. What's X?
X is
There's another percentage of S, isn't it?
Awesome.
Okay.
but it's just what you require the nodes to be. Like say you require each node to be 5%.
Okay, so S is not the cache. X is the cache.
Right.
All right. Your protocol has some values to it, right? You have parameters to your protocol. X being one of them.
I did it in math. I went back and replaced the math.
Ooh. X is one of your parameters for your protocol, right? Your caching protocol. Everything else is hope.
Basically.
Correct? Okay. All right, so we have X. X is a percentage. Again, X is a percentage of S. We have no way to make it, right?
Well, S is what you'll be tracking.
S is a local view of the. Okay, so S
And then X is randomly
Look.
chosen from that.
is randomly chosen. Okay, I see.
If that makes
It does make more sense. X is a percentage of S that you're choosing. X is a random percentage of S that you're choosing to keep. S is your local view of your local maxima of queries, right? T is some number that we don't have any way to claim. All I'm saying is X is, alright, X and S makes sense. T, not yet. But you're saying that S over T is a percent probability that X over S. X over S. It's X over S. X is a percentage of S, is a set, right? Or is a percentage?
X is a percentage.
S is also a percentage. Alright, when you say that S over T, S is a percentage, T is a percentage. S divided by T is the percent probability that X over S, what does that mean, equals?
This should be a fraction. It's still, I still want to be a percentage.
It is a percentage, right?
Say you said X is 5%.
Alright.
Then you have a probability that 1/4 of the nodes you're going to contact who have a similar view like you will.
Right. If X is 5%,
That's because S is 20%.
I've taken 5% of
20%. Or 5%. Sorry. 25%.
Yeah.
okay, so X is not a percentage of S.
We want
X is a percentage. You're claiming that X is a percentage of T. No, X is a percentage of all the queries.
We can look at it either way.
No, I need to look at it a particular way, otherwise it's a lot smaller. Alright?
Yeah.
So, you're saying that X is a percentage of all the queries. Okay, say 5%. Okay. Now, alright, so we're saying that since X is a percentage of S, you're saying that, yes, there is a percentage of all the queries that represents. It happens to be a percentage only selected from S, which is a selection that you're claiming is only selected from T. Okay, that's fine. Now, again, all of these relate to all the queries in some way, and that's probably what that number ends up being, right? Okay, because all of these are just percentage of all the queries, right? So you're claiming that T, S over T, in some way, like the ratio of S to T, is some sort of ratio of X to S?
Right.
Alright, that just means that you chose X to be that, right? Probability. Probability is, I think, funny. It's a proportion. Right? You're saying it's some sort of proportion, but this probability, how does that do with probability? Yeah, I mean it does, in the sense that if, but see, when you start talking about like probability, I mean that's really saying that there's some sort of uniform chance that we're going to choose any of them. You know what I'm saying? Just because I'm choosing 40% of all of them, you're not saying that the probability of that being the query that I'm about to service is that you're hoping that's not true. Right? So using that number as a number of 40%, your claim is that if I track 5%, my actual hits are going to be higher than 5%, right? Is that what these formulas are supposed to try and tell me? Is that here's how much better than 5% I'm getting? Huh?
Oh.
Okay, how?
Screw it. I'll model it and I'll come back.
No, but okay, no, because you need to be clear as to like what numbers here you actually need. All right. Yeah, T is some sort of, claim,
Alright, forget T.
right? What are these other things? Peers.
Peers?
Yeah,
Peers be...
the set of neighbors, right?
No,
Or all the peers. All the peers.
Total.
Possible queries. Where does that show up?
That would be just a...
Yeah, where'd
number of
that go?
files.
That's nowhere in those. maximum hops, diameter of the network, correct? Okay, diameter of the network is log VP, that makes sense. Require each, what in P?
What was that?
No, X is an element of P. Ugh. Overloading X. Alright. Each peer in P, right? Store X percent of S. Okay. I can accept that because S is a local view of top queries. X is a percentage of that. So X wouldn't be 5, right? X would be like in that case, 25, right? Okay, so 25% of S, which ends up being
Which is why I said you look at
5% of all. Now, and our goal is to show that by storing X, we get more hits.
Right.
Okay. Now, I mean, all right. I'll accept that X needs to be there since it is a randomly chosen selection of S. S is 20% of all.
or you can use some other smart method.
What's smarter than
Like better randomization.
random's fine. I mean, uniform random's fine. Just because if you're not going to query any of the other nodes, then you have nothing else to go on. Well, I mean, part of the claim is that this ranking that you have has some value to it. But uniform is good just because if you're saying that the top 20% is the best one to choose from, then it's the best one to choose from. So choosing randomly from there, you do have a chance of, if it's a uniform random, then all the peers choosing from that top 20%, then the real question is the real thing is that the S is different for each peer. S is different for each peer. Choosing the random selection from there, I don't know what the probability ends up being that you'll choose the same things as some of the others because you actually have a chance of choosing more of the same ones because if they're actually top contenders in the global T sense, then you're choosing things that everybody sees.
That's about right.
Huh?
That's about where I hit my wall.
Okay. So there's some sort of, the thing is S is different from T. We don't know how different it is from T. Your overall hope is that by choosing X% randomly from your S, is you're hoping to cover all of T. And your hope is that by choosing T, by covering T, you're actually going to cover more than 40% of the queries. More than T% of the queries. I'll accept that, yeah. I see what you're saying. See, your picture actually looks like this, though. Everything. Top 40%. It's not just that. Right? Here's the descending rank of top queries, right? You're saying I like the top 40%. Right? And then you have these S's, so that's the global view. Okay? Each of these nodes looks at some subset of all these queries, or ends up encountering them. Okay? Or at least that's a claim, right? So you're saying there's some percentage here, S. Okay? Which is cool. Right? This S, among all the peers, your hope is that all these various S cover T. Right? In some way, shape, or form. And then your other hope is this. Is that by choosing an X random sampling here, your other hope is that through all the X%, you're going to randomly cover all the S, which in turn is going to cover all of T. Your end goal is to randomly choose from some global T, hoping that you'll get it all. I don't know why all these numbers have to be different, though. You know what I'm saying? Why shouldn't S just be 40%, the same as T? Because it's not going to be 40%. It's not going to, even if you choose 40%, you're saying 40% of the things I see. I don't know. I mean, maybe making it smaller is better. I don't know. But again, it's like we don't really have anything to go on with that, right? I mean, we don't have anything to go on. It's like some higher percentage of the queries is covering it better or worse or whatever, right? But all I'm saying is, it's like, just think of it as like this is my mini view, my local view of everything, and I'm going to choose randomly because my theory is that everybody's local view, there's actually tons of overlap there, and by not choosing the same ones, I can store less, right? So that's what your goal is by doing random sampling as opposed to, the complete top percentage. Then this is what happens. But I mean, to be perfectly honest, if you claim that you're going to randomly cover all of T by using local, I mean, there might be benefit to just storing S, right? Store S because the randomness comes in the fact that you don't all have the same view of this.
Yeah.
But there is I don't know. There's something to be said about doing random sampling of S. I mean, there's something interesting there, I think. Like your idea that random sampling, you're reducing those number of redundant messages. You're hoping to get to it faster. In other words, get to the query faster by not having too many people store the same thing. You want a better spread, but I don't know. Be perfect honest, why don't you just start off just store 40% of the queries you see? You know what I mean? Because you know what that means, right? Yeah, I mean, you can definitely say that these are the top 40% of my queries, right? Store those, run it, see what it looks like, and then randomly sample it and see what it looks like. Because you're hoping to sample all of T. And I don't know what benefit there is to making S smaller in the sense that you're making it less likely that you'll cover. In other words, if you make your
That actually hurts my case.
your bullet smaller, it's like you're not gonna, you have less chance that you're gonna hit all of it. You're trying to paint the whole thing, and it's like by making your brush smaller, you're like making it harder on yourself trying to cover it. So
try that and try random subset.
It's actually easier. It would be easier to just say I'm going to look at my local top 40% because what I'm saying is the chance that you got the same 40% as the real T, that your S equals T, is a lot higher than your S equaling T if S is smaller than T. You know what I'm saying? You're introducing another element of randomness, which is hopefully my smaller S is covering different portions of this guy's smaller S, and that guy's smaller S, and that guy's smaller S. In other words, you have to be covering different portions for it to actually work. Whereas if you make S the same as T, or like your local view the same as T, you actually win in the case where your theory is true, right? Your theory being true would be all my local views of the top, 40% are the actual top 40%. So if I were to do random distribution there, I actually would cover the top 40%, right? Whereas there's only a chance that's true if you make S smaller than T. So I guess, the way to look at it is that S does look like what you've drawn, but not by changing its value to be different than T. You see what I'm saying? So S may end up being that small little circle. The only problem I see with that is that when you're right, you've introduced the possibility of being wrong. In other words, when your theory is actually correct, that looking at the local top percentage, you'll get the global top percentage. When you're actually right, there's still introducing this additional mechanism makes it so you could be wrong.
I just include my problem for myself.
Right. You introduce some additional kind of. Well, I mean, who knows? Maybe the thing is if it turns out that these two are so much further related, in other words, your theory's wrong, you would actually cover for it using this technique because you'd made the wrongness area small. In other words, by making S smaller than T, you've given yourself more wiggle room as to where it moves. See what I'm saying? So, through random luck, you might be able to do it, whereas by making it the same as T, you make it less likely if your theory's wrong. It doesn't show confidence, I guess is what I'm saying.
I'll come back with that.
No, but I mean, make S the same as T. Do random sampling. So I mean, the random distribution idea is good. Let's see what happens. But yeah, start off with that. Actually, again, start off without doing even random distribution and just see
Take
what the performance is.
X%.
Because random distribution is really to help you with storage. The idea is that
Reduce storage size.
the other thing you can do is, since you're, if you do simulation, is actually compare how similar S is among your peers. In other words, when you generate S, you run it for a while. Everybody's running queries. They're all storing S. Periodically sample and see how similar are all the S's. Because that can give you numbers as to say what X should be, what T should be. Because see, the thing is, when you're doing simulation, you can actually calculate T. See what I'm saying?
Yeah.
And then you can see how different are each of the S from T. You see what I'm saying?
Yeah.
So you can actually iterate through all the nodes and say, this one is 80% containment of T, 80%, 80%. If they all end up looking like 80%, now you have some numbers and you're like, oh, that's something. That's something I didn't know before. That by just running and storing the top, 40%, I actually cover, 30% of that area. Okay.
So
Hopefully, now he's got nowhere to run. He's gonna split his time between code.
That's all good.
Oh yeah, this different kind of code. Yeah. I like it, Ring. It's good.
Good first shot.
Hmm?
Good first shot.
No, good shot. Period. Not just good first shot. That's irrelevant. How many tries you've had doesn't matter.